To everyone who has dialed into the webinar so far. I'd like to welcome you today. We'll be discussing current sensing and electric vehicle service equipment. My name is Bart Basil. I'm on the Texas Instrument Systems team, focusing on grid infrastructure applications. Before we really get into the content of today's presentation, I want to give you a few resources in case you do have to drop off early. We have a few pages related to charging stations on the TI.com website. So these have full block diagrams and reference designs associated with both AC and DC charging stations. So if you ever want more information on these end equipment and applications, you can feel free to navigate to our applications pages and really dig in and see all of the associated reference designs and products that we recommend for these particular applications. In addition, the TI.com training portal and the TI.com reference library are full of great information, deep dives into specific subject matter, and a lot of additional applications that are in addition to current sensing. So please use those resources whenever you're working on your next design. Throughout the presentation, you're also welcome to use the chat box inside Webinar Room to ask any questions of our team here, and at the end of the presentation, we'll be going through and answering as many of those as we can. So please feel free to ask away. So in today's presentation, we'll be covering obviously the current sensing, and so we'll look at shunt and isolated measurement as well as some magnetic measurement systems. But beforehand, we're going to go into a bit of a system overview, looking at electric vehicle service equipment from a fairly high level and seeing where different types of current sensing topologies fit in. So to start with, there's generally two types of EV charging stations in the market. The way that they're normally defined is level 1 and 2, which are AC power delivery to the vehicle, and level 3, which is DC charging. Inside the level 1 and 2, the vehicle uses an onboard charger, and AC is delivered through a simple power control device for the EVSE. So it's really just a direct connection to the grid with some safety interlocks on top of it. These are typically in the 1.5 to maybe up to 20 kilowatt, depending on the voltage available at the charging station itself. Now, this onboard converter that's doing the AC to DC conversion needs to be fairly small, highly efficient, and automotive qualified since it resides on the vehicle. So to get around some of the limitations here for level 3 in the DC stations, we're pulling that AC to DC converter out of the vehicle, and we're able to really increase the power delivery capability by connecting the high voltage DC straight to the battery pack for charging. And so these are the fast chargers that we're seeing in the market. So this is 300 to 600 volts DC and hundreds of amps being delivered into the battery pack. And so for the bulk of our current sensing and the system complexity is really going to be inside these level 3 DC charging stations. So taking a little bit of a closer look at the different topologies we have, the AC chargers are fairly simple devices. There's going to be a basic power delivery control and system controller, but these stations still need to be able to self-monitor their own power consumption. So there's typically a power meter of some kind on the input stage before the power delivery control. So that system controller can determine exactly how much power is being delivered. On more advanced stations, it can do billing and things like that. For anything related to AC power sensing, we have a lot of e-meter reference designs that can plug right into these and give very high accuracy AC power measurement. On the DC charging stations, however, you can see that these systems are a lot more complex. So what we typically see in the market are AC to DC converters and DC to DC converters in series here, and then multiple smaller converters are put into parallel to generate this high voltage DC into the vehicle. So several 10 kilowatt power stages will be put into parallel to generate a 60 or more kilowatt power station. And then on the output stage of this, we also have a power meter that's measuring the total energy delivered into the vehicle. So if we look a little bit closer into these power conversion stages, on the bottom left here, we have the PFC. This is a standard Vienna rectifier topology. So depending on the particular topology and control algorithms used, the current sensing can go into a couple different places inside this station. So normally we'll have it on the AC input and use that feed that into the DC or to the DSP for the control loops. but also on the output, the DC bus of the Vienna stage will require some kind of current sensing. So the input on these is typically 400 volts AC with a current in the 20 amp range. And the voltage on the output is usually 400 volts DC with the same kind of current ratings. So these kind of loops require also a fairly high bandwidth sensing stage, and we'll get into more of those specifications later and why they matter. On the DC-DC, this is a typical LLC topology. So we can see the DC voltage coming in from the PFC and then being converted to whatever the vehicle is requesting. So the output on this could range anywhere from 400 to 800 volt DC with modern vehicles, and we could see this go even higher in the future. And then a similar range up into the 20 amp kind of range, depending on the particular design of the DC-DC system on these applications. We're going to look first off here at shunt-based measurements. This is probably the simplest form of current measurement that everyone is familiar with, but there are some particular things that need to be taken into consideration whenever we're looking at EVSEs. So here we have a simplified LLC, and you can see a handful of places inside a normal implementation of this converter where current sensing could be done. So we're going to look at a few of the key parameters for these different points inside the system and why they each matter and what contributes to some of the total error that we're going to have to see and mitigate inside the system design. So here we have a fairly comprehensive listing of parameters that we really care about whenever we're starting with low side sensing. So what we mean by low side is that the shunt resistor is placed between the system load and ground. So these systems are seeing fairly high voltages up into the 400 to 800 volt range, and whenever we have a common mode on the low side, we'll call that common mode 0 rather than the high voltage common mode that we'll talk about later. Some of these systems will also have inductive kickback, which can actually generate negative common mode. So on the low side sensing, it's important to have a common mode range that can support potential negative to avoid damaging any of the electronics in the system. These control loops also operate at fairly high frequencies, and as we're seeing in this market, these switching stages are starting to go faster in order to increase efficiency and reduce the size of magnetics. So bandwidth is going to be important here. Whenever we look at bandwidth on here, the difference in the different points inside the system is if we're measuring instantaneous or average current. So on the actual control side, we're looking at instantaneous current of the system, at which the DSP needs for the control loops. So we want a fairly high bandwidth here, usually in the 200 kilohertz or more range. And whenever we're doing average current, the bandwidth can be a lot lower. So this would be the input to the system if we're just doing bulk energy measurement, or the actual output to the vehicle where we don't need as fast of a response time. We can see directionality as a feature here. In current EVSE designs, we don't see a lot of bidirectionality, but there is a growing trend to do work and research into vehicle to grid. So this would support energy coming from the vehicle battery back to the grid in some instances. And in those cases, a bidirectional converter would need to be implemented and ensure that the current sensing is also bidirectional. An amplifier's offset is one of the most important things that's going to affect your accuracy inside the system. And really what it's defining is the smallest current that you can sense, or the smallest voltage across that resistor that's inside the system. In addition to offset, what's going to be important is also the offset drift. This is commonly an overlooked parameter, and as a system temperature changes, that drift can really impact the offset voltage and have a fairly significant effect on accuracy across a temperature range. And lastly, the gain of the system is how small of a signal that we can actually amplify and put into our ADCs inside the DSP. And so this is going to determine how small of a signal and essentially how small of a resistor that we can use inside the system. So looking a little bit closer at actually sizing shunt resistors, there's not a lot of complexity inside it, but there is some things to keep in mind. For this particular example, we're going to look at our INA28X family of devices. So these are integrated current sense amplifiers. We'll talk a little bit more about the features of these later on. This particular one It's fairly good for low side sensing inside EVSE. It has a negative 16-volt common mode, so it can support negative with the inductive kickback, and it has a fairly wide analog supply range, so plus or minus 5 volts. And then multiple gain configurations lets you size the shunt resistor appropriately. If you're interested in more of the 28X family, we do have a TI design, the TIDA 00302, which is a fully implemented reference for this particular device. And these TI designs show all of the design parametrics, cares and considerations when doing the design, as well as testing results. So you can really see the accuracy of this in hardware, not just what is expected from testing on the bench in silicon. So in order to size the shunt resistor, we do need a few pieces of information first. The load current range, which is going to be defined by the total system, and then the available supply voltage. And this will be defined by both the device and the system, so it depends on how your topology is affected by it. For this one, we'll use an example of supply volt of 5 volts, but it's important to remember that the device cannot fully go from ground to 5 volts as that we would feed it. There is going to be a window inside this. And for this particular device, it's about 40 millivolts from ground and about 40 millivolts from VS. So this gives our total supply volt of 40 millivolts to 4.6 volts. We're going to choose the 282, which has a gain of 50 volts per volt. So since the supply voltage is really going to dictate the output of our amplifier, we have to divide that by the gain to get the input range. So this will be 800 microvolts to 92 millivolts for this particular one. And from here, using our load range, so we'll use an example of 5 amps to 10 amps, that's going to get us our actual shunt value using a simple application of Ohm's law. So in this one, we can see at the high end, we have a shunt of 9.2 milliohms, on the low end of 0.16 milliohms. Now, it's important to note that this shunt value is directly related to both power and accuracy. So the power dissipation is sometimes overlooked inside these systems. If we look at this and choose the larger resistor, we can see that at 92 millivolts and 10 amps, we're seeing about a watt of power dissipation. So this leads to self-heating, and it could lead to inaccuracies inside the system. So it's important to balance this out. While we can ensure accuracy by choosing a larger resistor, the self-heating might be a detriment to the system and actually impact our accuracy and our granularity. So looking a little bit closer at accuracy, whenever we determine these for the current shunt amplifiers, there's 2 different ways to look at it. The worst case accuracy, which is essentially a sum of all of the inaccuracies inside the system, and then a probable accuracy, which is a root mean squared summation. So you might see both of these tossed around when looking at total system accuracy. Typically, what we're going to be interested in whenever we're designing an industrial system like this is going to be the worst case accuracy. Now, there's a lot of different sources for error inside these systems, but the 2 main ones are going to be offset error and gain error. And so the chart here shows a representation of the different errors and how they impact the system. So the differential voltage along the x-axis is essentially related to how much current we're sensing. So the voltage drop across the resistor. And then we can see the total error here. And as we can see, when the differential voltage is lower, a large gain or a large offset error can have a significant impact. So whenever it is so let's say a 1 millivolt gain error on a 10 millivolt signal, that's going to be a 10% error that's potentially injected inside the system. However, as our differential voltage increases, we start to see gain error become the primary contributor to total system error. So to help compensate some of these errors that we see, the TI solution is to use a dedicated current sense amplifier versus the traditional op-amp. So there's a lot of benefits to this. With the general purpose op-amp, whenever you're looking at the specifications for the Sphere system, everything is actually specified to the amplifier itself. It doesn't take into consideration any of the external passive components you need for your filtering. And so things like bandwidth and offset voltage are indeterminate for the system. So a lot of simulation is required to ensure that you can maintain accuracy across the entire system. In addition, the total system error, whenever you're using just a general purpose op-amp, even with precision passives, it can often be difficult to get it below even 10% in some cases, depending on the system and the op-amps chosen. So the current sense amplifier integrates all of the passives with the amplifier. So they have precision-tuned gain and offsets built into this, and we can put these passive components into silicon and make sure that they're high precision and that they're stable across temperature. So what this means is that all of the specifications are now including these passive components. We can reduce PCB footprint, and we can reduce offset voltage temperature drift, which is one of the primary contributors to error inside these systems. So by doing this, compared to a typical 10% error with the amplifier alone and precision passives, we can actually get much higher than that and achieve system errors in below 1%, even across temperature ranges for the system. So an additional benefit of this, we can see here with the traditional op-amp on the left-hand side, you can see that there's a lot of external passive components required in order to support that application. So in a differential measurement, which is fairly common on a shunt resistor-based system, we can see a minimum of 4 external passives. Each one has to be precision tuned. Whenever we integrate all of that into a single device, we can remove all of those passives, reduce footprint requirements, and move into a single package device. And so many of our devices are also sized to match a lot of the standard op-amp packaging. So you can just drop it in to your system to evaluate performance without having to worry about redesigning the entire layout. So this makes it really easy to evaluate. And as you can see here, the total footprint size is significantly reduced. So it keeps your design a lot simpler in the end. You can see here the differences between the two. We're going to be reducing the total overall error introduced into the system by integrating the gain resistors and by precision tuning this all in silicon so that we have a much lower voltage drift on that offset. In addition, one more thing, since we're doing all of this in silicon, it's capable of increasing the common mode range of that shunt resisting sensing element. So inside these systems, normally an op-amp would only have as much common mode range as the op-amp is capable of, so usually as much as your VS. Inside one of the current sense amplifiers, we can integrate a lot more into the package and increase that common mode range in silicon, and sometimes up to 80 volts, which can, on some lower voltage systems, can even enable high side sensing. Now, even though we can get it up to 80 volts, we can still see, though, that inside EVSEs, we're talking about 400 to 800 volts. So we'll talk more about those even higher common modes a bit more later. If you're interested in seeing some of the performance characteristics of these devices, we do have a specific TI design. This is TIDA 01141, and it uses an INA 240, and it pairs it with an LM393 comparator. And so this particular design is specified for plus or minus 100 amps and is capable of less than 1% error across a wide temperature range. And by integrating that comparator, it also adds in over and under current protection. So this design with the INA 240 is a really good solution for low side current measurement inside these power stages inside the EVSE. So feel free to check out this design. It has schematics, bombs, test reports, everything you would need to evaluate on your own. And all of the hardware design is available, so you can see the proper way to implement this in your system. So we have a few additional resources available for you if you're interested. We have a wide library of tech notes available around shunt amplifiers. So there are some that are specific for using them in power supplies and even how to pair them properly with comparators. So these are all available on the TI.com website underneath current shunt sensing. We also have an online training series dedicated to current sensing with shunt amplifiers. And so this is a full deep dive into the technology and design considerations taught by the experts here at TI. So feel free to watch those at your leisure. In addition, a really interesting tool that I like is the error estimation tool. Every single one of the shunt amplifiers comes with a chart that we can see here on the product page. So you can enter your system parameters, and it will estimate the total system error that you would have inside your system. So you can see really quickly at a glance if a device is suitable for your application. So moving on, we're going to explore what to do whenever that common mode starts creeping even higher. So if we can, in silicon, we can get common modes up to 80 or 100 volts in some cases. But when we're talking 400 to 600 volts inside an EVSE, we're obviously going to need something significantly higher. And so that's where isolated current sensing comes into play. So specifically here inside high side, we're looking at high side sensing. So this is going to be on the high end of either the input or output of a power stage used for current feedback. Now, whenever we talk about a few different current sense topologies, we have voltage output, which we explored a little bit with our basic amplifiers. We also have current output, which uses an output buffer transistor. And then these can be stacked in creative ways. However, to put these at high common mode, you're going to be reducing accuracy because of the external passives required. We also have digital outputs where our current shunt amplifiers are paired with an internal ADC. And then the output SPI or I2C bus can be digitally isolated. However, the internal ADCs on these don't have a lot of configuration options because they are highly dedicated for current sensing. So there are some limitations there. The preferred solution is actually to use a bit stream amplifier. So what this device will do is actually isolate the output of a delta sigma modulator. And so this isolated output is going to provide a very high common mode capability into your high side sensing application. So by doing this, moving the sensing to the high side, we can enable some additional features inside the system as well. So this lets us detect primarily errors. Specifically, we're looking at ground short errors. And so we couldn't actually do that on the low side because the low side sensor wouldn't be able to detect if the high side is shorted out. But we can do that here on the high side. So we can start adding in some protection features into the system itself. So we look a little bit closer here at the two different isolated amplifiers. So on the top, we have a dedicated amplifier by itself. So in general, this is an analog in and analog out with a full isolation barrier. On the low side of the isolation barrier, you can see that there's a fourth order filter and an oscillator, which is going to generate a clock that will feed a delta sigma modulator on the high side, and then the data output is passed into the fourth order filter. And then the output of this system can be passed through a simple differential amplifier and into the SAR ADC on a typical MCU or MPU used in your DSP calculations. And then we have that isolation barrier, which is on the newer devices is double stack capacitive, which can even get up to reinforced isolation. So we're looking at common mode capabilities in the 1.5 kilovolt for a design like this. Now, the other option is using an isolated modulator. So this essentially removes that fourth order filter and just feeds the bit stream out and takes a clock in from your MCU. So this simplifies the design, but moves a lot of the filtering to the MCU itself. So we can see on the top example here, that amplifier has 3 different conversion stages inside the signal chain. So each one is going to add its own gain and offset errors, like we talked about before. And then you also have any limitations on your SAR ADC. So the total system accuracy is going to be fairly limited, usually to about 10 bits of accuracy. When we move that filtering to the MCU itself, everything is done in the digital domain. So we have a single conversion stage done on the high side, and then everything is done digitally after that with hardware modules built into the MCU. And this achieves typically above 14 bits of accuracy. So we can see that the ENOB on these two systems, the isolated delta sigma modulator can be significantly higher. So looking a little bit closer at these, we're going to use one of the AMC 13XX family of devices. And so this particular one has a 50 millivolt drop across the input. And so essentially what we're going to do is tie that back to what we talked about earlier with our shunt sizing. So when we looked at our VS range divided by gain, we can just use the output of that system and use a 50 millivolt range. And so that's actually going to be a fairly significant reduction in power dissipation across that resistor. Depending on the requirements of the system, and if you do need a larger resistor and can tolerate the power losses, we do have options up to 250 millivolts, but you're able to tune that input stage. This provides an isolated sensing solution. So as I mentioned before, these can be even reinforced. So 1 kilovolt and above of common mode is no problem for these designs. The AMC devices also fully integrate the differential amplifier. So much like our current sense amplifiers, these are precision tuned in silicon to reduce offset and temperature drift error. And so rather than using an isolated ADC, we can have a fully integrated current sensing solution that is specific to the application and reduces any overall error. Now, commonly inside a system like this, we're going to have multiple converters or multiple high-side sensing elements with multiple converters. And so by having the digital in and out, we can actually synchronize all of the clocks together. And so that enables a single output from the MCU to drive all of these converters. And then they just have to read the data lines in. For longer boards, as many of you are probably aware, building a 10 kilowatt board they get fairly large. So we do have LVDS options in order to increase EMI robustness. One thing to keep in mind for these, though, since they are fully isolated, a bias supply is required to power the high side of the converter. And so this is some additional circuitry required, but we do have solutions that cover how to do a controller and LDO to ensure clean analog for the high side sensing. So if you're interested in seeing more about how to implement isolated amplification inside your solution, I can recommend this particular TI design, TIDA 00912. So this one is made specifically for motor drives, but it's a generic application. So it integrates a gain stage for an even smaller shunt. So you can use the 50 millivolt input and then have an even smaller range from your shunt resistor to reduce power draw. And it also shows how to use a proper gain stage on the output of that, since it's an isolated amplifier, so properly implementing an OPA 376, as well as all of the isolated bias supplies and LDOs to power the analog signal chain cleanly. So feel free to check out this design. Again, it also includes all of the schematics, BOM, and test reports from our labs here at TI. So there is another level of isolation available for even higher levels of current and higher levels of common mode if that's a requirement inside your system. And that's going to be magnetic measurements. So for these, we're actually going to be utilizing fundamental elements of physics and the magnetic fields generated around flowing current in order to measure the current itself. And so these are broadly looped into two different categories. So closed loop sensors, as we have here on the left, is going to be a loop around the current carrying conductor of some kind. And we have open loop current sensors, which we'll talk a little bit more about later. So typically inside these closed loop sensors, it's going to be a module type solution where a toroid is going to concentrate the field around the conductor. So the sensor will actually be integrated into this module itself, so the output will be a simple analog voltage that you can read. Let's look a little bit closer at how those are designed and how they're implemented. So this is a high-level overview of one of these current sensing modules. So we can see on the left-hand side the primary conductor here, which we'll be measuring the current of. Then there's magnetic shells around it that will concentrate the magnetic field that's being induced by that primary conductor. Now you can see there's a sensor placed there, which is going to measure the current. Now you would typically think that we would use the output of that sensor as our measurement device, but what's actually done in these is that there's a compensation coil that we will drive current into, and that will actually reduce the total magnetic field inside the shells to zero. And so what we're essentially looking at is how much current is required to drive that magnetic field to zero, and using the flux gate sensor as our reference point. And then we have an analog front end that will be measuring the amount of current through that coil and actually giving us the output here. So we're not directly measuring the sensor, but we're measuring how much current is required to bring that back to zero. So we have different applications for different amounts of this circuit itself. So we have products that cover just the sensor front end. So this would be an interface for the flux gate sensor, so it can be done externally, as well as that compensation coil. We have solutions that will integrate the FluxGate sensor itself, and then we have total system solutions that integrate all of this into one. So if you're interested in how to actually implement one of these solutions, there's a couple different options. You can buy a module that is pre-made and just drops into your board and integrates full magnetic sensing with the air gap isolation. Or you can go down the path of designing your own coils or having a third party do it and integrating your own system solution. So there's a couple trade-offs obviously between each one. Designing your coils is not incredibly straightforward. You do need to have some expertise in magnetics, but we have reference designs that cover a lot of this for you. So this particular one, TIDA 00905, goes through a lot of what is required inside these coils. So you can see the 3 magnetic cores on this board were actually designed by TI and a partner. And so we have all of the design files available for these. And these use the DRV 421, which is a fully integrated solution. So the coil is really just passing the primary current, and then we're measuring it with the 421 actually mounted to the PCB itself. In addition, this design will also show how to add in overcurrent detection, ground fault detection, so using comparators appropriately, the appropriate analog power for these kind of sensors, as well as some of the amplification stages required on the output. So even if you're not directly interested in designing your own coils, you do have the option to review this design, kind of see what kind of accuracies are available, and understand what kind of additional circuitry is required around these sensors. So next up, we're going to look at a really interesting application that fits well into EVSEs, and that's going to be open loop current sensors. So in addition to the magnetic field being generated around a conductor, we also have a magnetic field being generated inside a conductor that we can measure directly with one of our devices. So a traditional methodology of measuring very high value currents is to have a very large coil wrapped around a bus bar. So in this particular application, looking up here at the top left, this is designed for, obviously, it's thousands of amps in some situations, but we see the amount of physical requirement to actually measure this. And so the new approach that TI has been working on for the last few years is actually integrating the sensor into the bus bar itself. So using a very small PCB and injecting the sensor into the middle of a hole drilled through the bus bar. So we can do a few extra things with this. One is we can increase immunity by actually using 2 devices. And so any stray fields are effectively canceled out, and we're only measuring the fields generated by the bus bar. Since the amount of electronics required for this is significantly reduced, it has a much lower power requirement. And one of the main things is just how compact this is. So looking at measuring something in the 200 to 400 amp range output of an EVSE. So whenever we parallelize all of those power stages and look at the total system output, something like this can fit very well, especially as EVSEs start growing in power output. And even with the amount of current and with the size of this solution, we're still able to see less than 1% error over a very, very wide dynamic range. So this approach is really interesting for a lot of different reasons, and we actually have a lot of supporting material to help you design something like this. So we understand that this is a fairly new topology and a new way of measuring high levels of current. And so to support that, we've put together a full application report on the theory of operation. So this goes over all of the magnetic sensing elements and what goes into designing a system like this. So how to position the hole, how big to make it, and then even designing the PCB, placing the DRV devices inside it. And we have associated magnetic field calculators for all of it, so you can see exactly how much magnetic field is being measured and how your system will respond to it. In addition, we also add the Busbar design simulator. So this is an FEMM script, so you can insert your particular design specifications and see exactly what kind of field strength you're going to have inside your conductor to make sure it's a good candidate. So using this, you can get the exact level of magnetic field inside the hole or slot in the bus bar, and you can simulate, before even trying to manufacture anything, to see if a solution like this is acceptable for your particular application. So this is a really good tool to play around with and really visualize exactly what's going on inside this Busbar application. The other option, if you don't want to go through and simulate everything, is we do have an available EVM if you just want to play with it. So it's TIPD205, which is orderable on TI.com. And as you can see here in the bottom left, it's actually a full Busbar implementation. So this is designed for about 110 amps of AC or DC with the small PCB and the hole that is associated with the inserting the sensors. And so you can actually order this and play around with the system. In addition, all of the design files are available again. So if you want to see how this works inside your solution, you can go through the TI design and understand exactly how this would work for your particular application and if it's implementable. So in addition to that, we do have a tech note covering all of this as well. So just like the current shunt amplifiers, this tech note covers a lot of different information regarding all of the magnetics and stray field rejection for your application. So feel free to go look at that as well if you want just a crash course inside this application. So to finish up on our overview of current sensing, I wanted to give you a few more resources. Again, I mentioned a few of these at the beginning, but I know that some of you may have joined late and might have missed them. So first off, we have application pages covering both AC and DC charging stations. So these application pages on TI.com have full block diagrams for AC for both of these charging station topologies. And on each of them, you can actually go and click into specific subsystems and see relevant TI designs for each one. So this particular example is a DC charging station. And so for each of the power stages, the HMI modules, any current and voltage sensing, we have relevant TI designs and specific products for those particular subsystems. In addition, any collateral associated with this particular application is available on there, so you can go and browse through any associated app notes or white papers or blog posts that might give you more information on these system designs. AC and DC charging stations are obviously not the only applications we cover. TI has hundreds of applications that we look at on a regular basis. And so if you have other things that you're working on, other projects, feel free to check out our application design pages. And hopefully you can find something useful there to help with your next design. In addition, the TI Designs reference library. So we currently have about 1,600 different TI designs available. I covered a few of them and mentioned earlier, but all of them include full schematic, BOM, design guide, and test reports to help with your application. So you can evaluate a part before even putting it into a system. And so what we do is we do our best to simulate exactly how you would be using this product inside your application so you can get an apples-to-apples comparison of what you would expect from a result standpoint. And these don't just cover current sensing, obviously. 1,600 designs. There's designs for wireless communication and PLC and motor drives. It covers the entire gamut of electronics. So definitely worth checking out. And we also have the TI.com training portal. So I mentioned this earlier with the Shunt training series, but there's a lot of other good material here for the entire signal chain. So definitely worth checking out the TI training portal. There's a lot of videos to go through. I personally can recommend the Precision Analog training series. It's been very good for learning and brushing up on some op-amp technologies and stability issues. So that covers the core of the presentation today. Thanks everyone for joining in with us today. We're now going to move into the QA session. So for any questions that were asked during the presentation, we'll go through those and hopefully have some good discussion regarding those. And so we actually have a few questions that were asked beforehand via the registration. We're going to cover a few of those questions right now. The first one that we have is, I was asking, how is a delta sigma analog to digital converter better than a standard SAR ADC. And so we talked about those with the isolated sensors, the ANC series. The high side is actually a delta sigma modulator, and then that bit stream or the amplified output is still a result of that conversion. So the delta sigma converters are typically a higher effective number of bits, so we're going to get a lot more accuracy out of those, especially when we start looking at very low offset voltages on the input of the converter itself. That will also see a lot higher stability out of a delta sigma converter. However, there are some trade-offs, which will be high cycle latency and a lower bandwidth. So these will typically have a bandwidth, especially inside these isolated ones, peaking out at about 200 kilohertz. And so that's worth keeping in mind if that's part of your design. If you do need incredibly high bandwidth on your system, a delta sigma converter might not be the most applicable measurement device, but there are low side delta sigmas that can go much higher, even into the megahertz. So if you need the really high ENOB, then the delta sigma is definitely the way to go for these. And so we had another question that was asking for the best practices for DC current that is not resistive. So really the only solution for DC current sensing that doesn't include a shunt resistor is going to be using a flux gate sensor. So there are topologies that use Hall effect, but these are fairly limited with their accuracy. So they can be a very tight package and they can offer some good isolation. However, the accuracy suffers inside a Hall effect sensor. So when using a flux gate sensor, I covered that one TI design earlier on. However, we do have a few others if you're interested in exploring them. So if you go to TI designs and search for flux gate, you can find quite a few. TIDA 00201 and its companion 208 show how to use the third-party flux gate modules and all of the associated analog circuitry around them. So definitely worth taking a look at if you want to know more about utilizing those inside your system. We had another one regarding the reference software needed for a 7.2 kilowatt onboard charger. We do actually have, I spoke a little bit earlier about the two different topologies, so Vienna rectifier and an LLC for the DC-DC stage. So we have reference designs for both of these that are directly applicable. They would just need to be scaled up for your particular application. And so TIDM-1000 is a Vienna rectifier, so it's a fully realized polyphase AC to DC converter. And TIDM-1001 is the associated LLC for that, for the DC to DC conversion stage. There was another one, we didn't really get into this, but the question regarding some information about the different standards for EV charging. And so whenever we look at the AC chargers, those are actually fairly standardized around the SAE J1772 version of the charger. So it's a multi-prong plug, and it's a simple pilot communication. So this is for level 1 and level 2, and there's variants of it around the world depending on the region, but it's generally the same. There's a very simple pilot wire and then AC power delivery to the vehicle. Now on the DC charging station side of things, it's a little bit more complicated currently. So there's several different standards that are available. So the first one is called CCS, and so it's an evolution of the J1772 connector style, and it's run by the group CHAR-IN, and so they're actually still working on designing and specifying this. And so it uses a broadband power line communication over the DC bus for the high power and high speed negotiation. So that's the CCS standard. The alternative to that currently in the global marketplace is a standard called SHADAMO, and they are very similar as far as the AC or the DC output of the station. However, the communications topology is what's going to be changing. So SHADAMO will be using CAN as its output rather than PLC. So whenever we look at those from a power conversion topology design, the actual AC to DC conversion is going to be essentially identical. So the only changes between those two is going to be the communication and the physical interface between them. And that's going to be primarily run by a system controller, not the actual DC-DC converter itself. And so there is one more, it's a little bit more, I guess, esoteric of a question, but it's using bidirectional charging for the vehicle. So what this is talking about is pulling battery or energy from the battery and putting it back onto the grid, or into using it as a home energy storage solution. And so there's a lot of different topologies that are being proposed for this particular system. And so it broadly, though, falls into two categories, where we'll have essentially an AC coupled system or a DC coupled system. So if we look at the future kind of AC coupled system, everything will have a directional DC to AC or AC DC converter, or it could be bidirectional. So your vehicle would have a bidirectional AC DC and DC AC on it. When we look at the charging station itself, the Vienna rectifier and the LLC are not directly suited for those, but we do have topologies that can be bidirectional for full power conversion. So whenever vehicles start supporting power export, that kind of topology can be added on. But since there's not really a core standard around it, then once those are defined, though, we'll start seeing what that communication looks like and how that will tie into larger energy management systems. Now, a DC coupled system is going to be a little bit more tightly closed than an AC coupled system. So in an AC system, all of the different things, so your solar inverter, your home energy storage, and your vehicle will just connect to the grid and have some kind of communication on the back end. In a DC coupled system, essentially what we'll be doing is having DC-DC converters on the front ends of all of these, and then a centralized bidirectional AC-DC converter. And so that would require, again, a fairly tightly coupled system. There's not really a standard around that at this point, but it's something that we might see emerge in the future as a lot more of industry goes to DC systems, as we're starting to see. So getting into some of the questions that were asked during the presentation today, the first one we have here is, what is the reason for the necessity of high bandwidth? And I mentioned 200 kilohertz. So the bandwidth on here, whenever we talk about 200 kilohertz, at least at that level, is going to be the instantaneous current measurement. So whenever we're running these high power converters, there's typically, again, a DSP that's doing all of the calculations and running all of the control loops in real time for the Vienna or the LLC. So to feed this control loop, we need a fairly accurate but instantaneous current measurement, because it's going to be needing that to determine how to control the system next, so which best to turn on and off. Right now, those power stages run, at least for the anything involving AC, is usually around 15 to 20 kilohertz, and then we see the DC stages in the 100 kilohertz range. And so for the AC stages, whenever we're running those systems, we usually want to be able to measure the DC current at the frequency of our control loop. And so if our control loop is running at 20 kilohertz, we can apply a simple Nyquist to say that we really want to be measuring current at 40 kilohertz, and usually we want to go a little bit higher than Nyquist, because that's going to be the most conservative for us. So whenever we're looking at DC-DC stations, however, if we're switching at 100 kilohertz and our control loop is running that fast, then we're likely going to be needing a measurement frequency in the 200 kilohertz range. And one of the things that we're actively working on here at TI is actually, how do we switch these even faster? So it's definitely worth looking at some of the emerging technologies around silicon carbide and gallium nitride switching. And so these switches have a much higher electron mobility, which enables them to switch much, much faster. And so instead of switching at 100 kilohertz for our DC-DC stage, we're actually looking at going up into the megahertz range. And so this is going to take a completely different topology, but in the interim, when we look at something like silicon carbide for an AC to DC stage, we can start switching these at the 150 kilohertz range. And so we're going to be needing signal bandwidth inside the 200 to 300 kilohertz range in order to effectively run these control loops. So we have another question here. So for a high-powered DC charging station, about 120 kilowatts, what would be the recommended setup for the shunt resistors or flux gate? I'm interested in knowing how the dynamic range of current will be handled, say 120 kilowatts at 400 volts, so 300 amps when the battery is empty, but only 10 kilowatts for when topping up the battery whenever state of charge is reached. So what this question is referring to essentially is the tapering off of the charge profile. So the lithium-ion batteries inside an electric vehicle don't charge at 100% capacity. So they'll start at fairly high capacity of charge. So this 120 kilowatts will be, let's say, the first half hour. And that's whenever we talk about these things and you see them in the marketing, it's the 30 minutes to 80% charge. And so that's the 120 kilowatt stage. So that can get us to 80%. But after that, we need to start slowing down the charge. And this is just part of the charging profile controlled by the battery pack management inside the car itself. So we'll slow down to something like the 25 amps, like mentioned here. Now, the question is, how do we maintain essentially dynamic range across both of these particular topologies? So when we look at the two of these, we have 300 amps and 20 amps. So the voltage will be the same on both of them. Now, while that obviously might seem fairly divergent, they're actually not that far apart. Whenever we look at total dynamic range of these sensing applications, we're looking at usually in the 1,000 to 1 or 2,000 to 1. So you can get a lot of granularity out of both a shunt resistor or a flux gate resistor. So what I mentioned a little bit earlier on, it was kind of quick, but if we have an external isolated modulator on the high side, the example showed about 14 bits effective on that measurement, which can get us a significant amount of granularity on the actual measurement itself, even across the full dynamic range. So from 300 amps to 25 amps, we're looking at a 12 to 1 change on that, which is not actually that high. Now, when you take this inside a typical charging station topology and you put all of the power modules in parallel, we're actually going to be reducing that even further. So we might have 5 different power modules, which would put our effective range at 60 amps to 5 amps, but that same dynamic range is there. So with the shunt resistor sized appropriately, it will still work well across both the high power and the low power cycles on the vehicle charging. So we have another question regarding the actual traction inverter. So what particular solution is recommended for traction inverter applications? And so for those that aren't 100% familiar with the EV itself, so we've been talking about external components. How do we actually get power from the grid to the vehicle? What this is actually concerning with is getting the power from the battery to the motor. And so most of these motors are going to be ACIMs, which do require power electronics and an inverter on the vehicle itself. So while my team does not work directly with that, we work more on the charging side and power conditioning for the battery. We do have a full automotive systems team here at TI that is focused on looking at exactly this. So traction inverters as well as the rest of the powertrain for EV and HEV. So if you want more information about traction inverters, I would recommend going to ti.com and underneath applications, going through the automotive section. So just like we have the TI designs and reference libraries and block diagrams for charging stations, we do have the same for traction inverters. So definitely worth checking out. There's a lot of great information there from that entire team. So they have a lot of good reference designs that are specific for automotive as well. So you'll see a lot of motor drive designs, which is obviously a big deal. 70% of the world's energy is consumed by motors. We work a lot with motor designs, and then also the automotive version of those is available for you to go peruse. So we have another question, and it's asking for just what's the best practice for current measurement? So that's kind of a nebulous question, but it's really going to depend on the system itself and exactly what it is that you're trying to achieve with it. So there's a lot of different considerations that go into play here. So whenever you're looking at your PFC stage, so that Vienna rectifier, we have AC input on the front end at about 400 volts of common mode, and so for AC, there's a lot of different topologies compared to DC. So you might be using a current transformer or looking at magnetics for that since it is grid connected. And then on the output, we're looking at shunt is fairly common for the outputs of those kinds of power stages. But again, depending on the requirements for it, the flux gate modules would also be acceptable for that. Both work well in application. So there's a lot of design trade-offs between these, obviously. If you're looking at a shunt with an amplifier, total system cost is actually fairly low. The magnetics option does significantly increase the cost of a solution, but the trade-off there is that it could be reduced design cycles, reduced design time on these. So these are the kind of questions that need to be asked whenever going through some of these design considerations. There's always a lot of trade-offs whenever you're doing current measurement and looking for different sensor topologies. So we have another one. So what are the physical design considerations for the shunt resistor of a 120 kilowatt, so we're looking at 400 volt, 300 amp fast charger? What is the approximate power dissipation of the shunt? So this is another one where we have obviously, there's some design challenges that come into play here. So when we look at the typical EVSE design, we have multiple power stages in parallel. So if we're looking at 120 kilowatt, typically we can see in those would be either 10 kilowatt or 20 kilowatt power modules themselves. So this would be, again, a dedicated AC to DC block with a Vienna rectifier and an LLC inside one module. And obviously, again, depending on the station design, who's doing the power supply design, these can change pretty drastically for the particular architecture. So when we're looking at a small subset of one of these, we can take, let's say, a 20 kilowatt charger, and we can reduce, so that would be, for this particular design, we would be at a factor of 6. So we're looking at about 50 amp output for these. So you need a shunt resistor that can handle 50 amps of current through it, which is pretty substantial. So this is one of those types of stations where you might be looking more at the flux gate. If we reduce that down and we start looking at something in, let's say, the 20 amp range, so then at that point, that's more within the realm of what a shunt can easily handle. For one of these designs, the approximate power dissipation really needs to be balanced out here, and that's what's going to define the size of the shunt resistor that you choose. And so what we normally see is that we want to try to keep that well below, 10 watts is going to be on the high side of this. So you'll have to check the packaging of the shunt resistor family you're looking at. There's a lot of different ones available, and it really depends on how much you're willing to spend on a shunt. I've seen some surprisingly expensive shunt resistors available on the market that have dedicated Kelvin connections for higher accuracy and things like that. But usually what we want to see is a power dissipation of about 5 watts, and that's less for wasted power and more for looking at the actual heat dissipation of the shunt itself. So the more heat dissipation in your system and the more losses, then that's going to result in additional inefficiencies and inaccuracies inside the solution. So it looks like we're out of time for today. If we didn't get to your question on the webinar itself, we'll be reaching out to you directly and with a response and an answer, so you can look forward to those. In addition, the presentation will be available online, so if you want to go through and review anything, all of the slides will also be available alongside it. So if there's any links or TI designs that you might have missed, you can feel free to go peruse those at your leisure and brush up on it. And again, feel free to check out our applications pages, the TI.com training portal, as well as all of the TI designs that we have available for you guys to look at. Thanks again for joining us. We really appreciate you spending your time with us here today at TI.